Hi everyone, I'm Mr. H, and this is a Sinusoidal Functions complete unit review. We're going to look at all the topics you see there in front of you, and we're going to do that through the lens of looking at three big questions that are going to bring all this together for us. This question says, state the transformations in the order that you would apply them required to graph the sinusoidal function shown. Describe what this does to the amplitude, period, starting point, and equation of the axis. Graph the transformed function. The first thing we want to do in order to understand how to graph this and transform it is to remember what the cosine function looks like. That's the parent function here that we're transforming. The cosine function has an amplitude of 1 and it has equation of the axis at 1 and a period of 360, and it looks like that. So what we're going to do is we're going to apply the transformations that are in the equation to that cosine function. It's also good to keep in mind what the sine function looks like. We're not going to use that here, but it is very similar to the cosine function, and it looks like what you see there. It has an amplitude of 1 as well, and a period of 360, and an equation of the axis at 0, but you'll notice that it starts at the equation of the axis and goes up from there. So let's compare this now to the transformed function. So in general, the transformed function is y equals a times cos of k x minus d plus c. So a is -4, which means it's a vertical stretch by a factor of 4. In other words, we're going to take the y values and multiply them by 4, but it's also negative. So not only are we going to multiply it by 4, we're going to multiply those y values effectively by -4. We're going to vertically stretch it by 4 and flip it over the x, the horizontal axis. The next thing to look at is the k value. And the k value here is a third. What that means is that we are going to do a horizontal stretch or compression. Now the tricky thing about k is it's always the reciprocal. So let's figure out what the factor is here. It's the reciprocal of 1/3, which is 3. So that means it's going to be a horizontal stretch. Horizontal stretch factor of 3. So instead of a period of 360, it's going to have a period of 1080, which we'll get to shortly. The d value is 120. It's positive because notice it's x minus d. X minus 120 up above. So that's a positive 120, which means it's going to shift positive 120 degrees to the right. And the last thing is the c value. The c value is just 1, which means it's going to shift the whole graph up by 1. So with all that in mind, let's go ahead and talk about the amplitude now. The amplitude of this function is going to be equal to 4. That's directly related to the a value. It's the magnitude of the a value. We'll deal with the negative shortly, but the amplitude is going to be 4. The period, I already alluded to, is the normal period of 360 multiplied by 3. Well, why is it multiplied by 3? Well, the period and the k value are reciprocals of one another. So effectively, you're taking the 360 degrees, you divide it by a third. That's the same thing as multiplying that by 3. And so that gives you a period of 1080 degrees. So there's your period and your amplitude. And so now let's look at the starting point. Because it shifted 120 degrees to the right, what that means is that it's going to start at 120 degrees, but keep in mind it's flipped over the x-axis. It would normally start at a maximum, and so because of that, it's going to start at a minimum at 120 degrees. The last thing is the equation of the axis, and that comes from the c value that shifted it 1 unit up. The normal cosine function has an equation of the axis y equals 0. This has an equation of the axis y equals 1. So we have all those properties now, and we're going to work together to graph this. Now, we could graph this using normal transformations, just like shown in front of you. But what we're going to do here is we're going to allow this to show us how to create a box that is going to fit exactly one cycle, exactly one period. So we're going to start at 120 degrees, and that period is going to end 1080 later, so it's going to end at 1200 degrees. So you can see there that my scale on my x-axis just is not going to fit. So what I'm going to do is I'm going to go ahead and change that scale to make it a little better to fit the numbers here. So I'm going to go every 3 squares is going to be 120 degrees. So it goes 360, 720, 1080, and 1440. And so I'm going to start by drawing my vertical values of the box. So my c value is is 1, so that means the equation of the axis is y equals 1. And in order to make this fit, because I'm going to go 4 above and 4 below that, I'm going up by every square being 2. So I'm going from 1 to 5 because my amplitude is 4. So that's going to be the amplitude above the equation of the axis. And then I'm going from 1 down to negative 3 because that's my amplitude below the equation of the axis. And so I'm just drawing those as dotted lines. And the top line is going to be the max. The bottom line is going to be the minimums. And then that middle line is the equation of the axis. So now I'm going to add the horizontal values. I know it starts at 120 degrees. It's 1/3 of the way to 360. And it's going to end at 1200 degrees. It's 120 past 1080. And so that's the beginning and the end of my cycle. And so the reason we call this the box method is what you see highlighted in front of you. That is a box. And that is going to fit exactly one period inside that box. So what we have to do with that box is we have to split it in half. We have to find the midpoint of that box, which is 60 less than 720 there. So it's going to be at 660 in that case. And then we have to split that up, and you can do that based on squares or based on degrees. What I'm doing here is I'm seeing that there's 9 squares from the beginning to end, so then 4.5 to the middle, and then 2 1/4 to each of the other quarter parts of this function. The key to remember is that every period has 4 quarters to it. And so if it's starting at a minimum, then it's going to go to the equation of the axis, is going to the maximum, back to the equation of the axis, and then back down to the minimum. And I can draw my curve through all those points. And what I have is I have exactly one period of that function, y equals -4 times cos of 1/3 x minus 120 plus 1. The key to keep in mind here is that I'm graphing all this in degrees. And so if you're doing this in radians, it's the same idea, but we just keep in mind that instead of 360, we have 2 pi on the x-axis. This question says, determine the new coordinates of the point 7, 0 after a rotation of 235 degrees about 0, 0. The first thing to remember is that we always start any angles at the positive x-axis and we go in a counterclockwise direction around. So 235 is between 180 and 270, and we can draw it in that quadrant like shown. So what we're doing is we're taking a line that started at the positive x-axis, and it had an endpoint of 7, 0, which means that that length of the line is 7, and we're turning it all the way around into this quadrant down in the bottom left. That's going to have the same length of the line, of that terminal arm we call that, and so that's still going to be 7. And what we're trying to do is we're trying to figure out the coordinates of that point at the end. Well, notice that this forms a right triangle, and we have an x and a y coordinate. Now they're both going to be negative here because the x value is negative and it's also below the x-axis, so the y value is negative. So what I'm going to do is I'm going to call this angle here the related acute angle. And this forms a right triangle down there in the bottom left quadrant. And so in order to find what beta is first, I'm going to take the 235 degrees and I'm going to subtract 180, and I get an angle of 55 degrees. And so now what I have to do is I have to go ahead and think about what this is in terms of a right triangle. And I'm just going to take the right triangle that we have and just bring it over by itself so we can focus in on that right triangle. So that we know the angle is 55 there, and we know that the length of the hypotenuse is 7. Now, sine of that angle, the related acute angle beta, is going to be equal to the opposite side, the y coordinate, and we're going to focus in on the magnitude of the y, so just the value. We're going to not worry about the negative part right now, divided by the hypotenuse, and the hypotenuse is r. So we rearrange this by multiplying both sides by r, and we can sub those numbers in. We have 7 as the r value and 55 is the beta value. And so that tells me that the length of y, the magnitude of y, is 5.73. So if we go back over to our picture on the left, we know that's a negative value, so it's negative 5.73. Again, now focusing on that triangle that we have in black there, we take the cosine of that related acute angle, and that's the adjacent, which is the length of x divided by the hypotenuse, which is r. So we rearrange that for the length x. We sub the numbers in, 7 times cosine of 55, just like we did previously, and we get the length of x to be a length of 4.02. So now we go back to the diagram on the left, and we recognize that that x value is not just 4.02, it's negative that, and so we label that, and we can now list our point. The point is the x value followed by the y value, so it's negative 4.02, comma, negative 5.73. 3. And that's all there is to it. This question says 2 white marks are made on a car tire by a parking meter inspector. One mark is made on the outer edge of the tire. The other mark is made a few centimeters from the edge. That doesn't mean 3. We have to interpret it based on the graph that we see there. The 2 graphs show the relationship between the heights of the white marks above the ground in terms of time as the car moves forward. Based on the graph, fill in the chart. Well, the first thing to keep in mind here is that the black mark, this is the mark 1, is going from 60 down to 0. And the other mark, mark 2, is going between 10 and 50. And so when we go ahead and we write the diameter of the circle the mark makes, the mark 1 goes from 0 to 60, so that's 60. And then the other mark going from 10 to 50 is going to be 40. Now the equation of the axis is the same for both of those. It's the center of the wheel. And so that's going to be at a height of 30 centimeters because the outer edge is going to go up to 60 and all the way down to 0. 30 above and 30 below that. So that's going to be the same for both of those marks because that's the middle of the wheel. The next thing is looking at the mark radius. So how far it is from the center of the wheel, the equation of the axis, up to the max or down to the min. And so in the case of mark 1, it's 30 centimeters. In the case of mark 2, it's 20 centimeters. Now we look at the period that this takes to go all the way around. Well, you can see that regardless of what function it is, they have the same period because they're going to take the same amount of time because they're at the same point on the wheel to go all the way around. So the period is 0.25 seconds to get from a minimum to a minimum, and then another 0.25 seconds to get the next minimum, etc. The circumference that the mark travels is going to be different because the inside mark is going to go less distance than the outside mark. But the circumference is always measured by taking pi and multiplying it by the diameter. So pi times 60, we end up getting a value of 188.50, and that's units of centimeters because this is a height of the mark in centimeters. And to calculate the circumference of the second mark, the diameter of that was 40, so pi times 40, which gives us 125.66, again, units in centimeters, 125.66 centimeters. So now we go ahead and we figure out the speed of the mark. Well, how do you find the speed of anything? Well, speed is simply distance over time. We see that driving down the road. We see kilometers per hour, so distance over time. So that means that if I'm finding speed in this case, the distance I can think about is the circumference because that occurs every period. That's a distance, circumference, and the period is a time. So I can make my speed my circumference divided by my period. So my circumference is 188.5 divided by a period of 0.25. And it's important to keep the units in mind here as well. It's centimeters per second. And that's going to give us 754 centimeters per second. 754 centimeters per second. Now to change centimeters to meters, we could divide by 100. And so this would give us 7.54 meters per second. We do the same calculation with the second mark. And because it's more inside on the wheel, it's going to move slower. So we have a circumference that's smaller divided by the same period as the other value. And so we end up getting a value of 503 centimeters per second. 503 centimeters per second. Again, 5.03 meters per second if you were to do that. So the thing to keep in mind here, and just it might be helpful to see a picture of the wheel. The wheel goes from 0 all the way up to 60. And then we have this, the equation of the axis is right in the middle. And then we have this mark on the wheel. And that mark is going to go around, not quite down to the ground. It's going down to 10 and it's going up to 50, down to 10 and up to 50. And so the closer you are to the inside of a wheel, just like a merry-go-round if you were on a playground as a kid, closer you are to the middle of the merry-go-round, the slower you're going, because if the further out you go, the more distance you have to travel, the bigger circumference in the same amount of time, the same period. And so that's why the speed of that inside mark is going slower, has less ground to cover in the same amount of time. So if you're ever on a playground again and you're on a merry-go-round, if you want a thrill, go as far to the outside as possible. If you're not up for thrills, either don't get on or go close to the middle. I hope that was helpful. And if you want to know more about how to analyze graphs of sinusoidal functions, check out the video on the left. For lots of videos about sinusoidal functions and the unit related to that, you can check out the playlist on the right. Thanks so much for watching.